Welcome to another deep dive, another week here, another deep dive. Today we have one Mr. Big Time, better known simply as Mick, and our next guest, he needs no introduction, Mr. Fabulous himself, Chance Ferro. Super thrilled to have both of these guys on with us today. And we're talking about the brain, keeping with the theme of new Epic just got launched. We're really, really excited about that. Our suspension team has done a ton of work. And we want to talk about the brain, how it started, what it has been, how it's evolved, what have we learned, and what brings us to the latest iteration, and how the new crop of sort of young visionaries have taken this time-tested piece of technology and really helped to advance and evolve this to meet the demands and the rigors of the latest riders and the way that we are using and experiencing trails and racing cross country and all of these things. So, let's get into the brains of this thing. I'm super thrilled. Thank you guys both for being here with us. And like I said, we launched the new Epic and the all-new brain, the fastest responding, the toughest shock we've ever made. The bike looks great. Everything looks fantastic. It rides like an absolute dream. But it's been a long evolutionary process, as things tend to be, to get us here. And so this is where I really want to bring in Mr. Mick, and we'll talk about kind of where we started, which is from really maybe an unlikely source, but I have right here just a little talking point of maybe where the brain first started. So Mick, can you tell us what we're looking at here and how one sort of maybe ill-fated trip ultimately served as the catalyst for developing, this product?
Yes, for sure. Okay, so what we have here, and this bike was ahead of its time. I think we introduced that bike in 1999. It was the FSR-XC. And really what we were trying to do with that bike, if you go back into the mountain biking history, you had a lot of people, anybody that was riding really cross-country type mountain biking was riding a hardtail with a suspension fork, and a lot of people were still riding just hardtails with rigid forks. Anything with suspension, full suspension, was still kind of contraption-y and really difficult to pedal and ride and stuff. So you definitely had the two camps, the early gravity set and then everybody else that was mountain biking. And so, Specialized was pioneering with this XC, because what it was is it was a lightweight full suspension bike, and it was targeted at cross-country riding. And it was really, really a neat bike. It was fun because it brought kind of full suspension into that mainstream market where a lot of people were riding mountain bikes. So with that, the team here thought it would be great because we had a factory cross-country team based out of Europe, and it was like, let's get the cross-country team to race this thing. And so I was sent on a mission it was probably early 2000, but I had to go over to the team camp and convince this European team, which were all roadies that started riding, XC, right? So none of them had ever ridden full suspension, and some of them were still having a hard time with a front suspension fork on their hardtail. I was challenged with going over there and testing these guys and convincing them the merits of full suspension and decoupling rider's mass from the terrain, the whole momentum carry, all the things that we knew suspension would do to make it faster. And so off I went. Luckily for me, the team camp was in Mallorca, Spain. That's a beautiful island out there in the Mediterranean. So
yeah, you were roughing it, huh?
So I set up a bunch of tests. It's similar to what Chance and I do now. It's how we test products. It's what I my motocross days on setting up bikes and stuff. So I went out, found some test sections, took the team out, and we started running these sectors with the full suspension bike, that FSR-XC, and then they would run it with their hardtail. And we were, we had a start to the section, an end to the section, and we were timing everything. So at the end of the day, we looked at everybody's times, and all of the riders were consistently faster on the full suspension bike on this gnarly little technical trail that I had them riding, because that was the best case to showcase what full suspension could do as far as, you know, keeping your forward momentum going under power. And so I thought, okay, I might have a chance at this, right? So we sit down, we're looking at all the results. Yes, they were faster. Yes. And they go, oh yeah, that's interesting, Mick. Yeah, that's, oh. And I said, okay, so will you guys race it? And they're like, no. And Luca Brumati, I think is the gentleman's name. He was our cross-country rider from Italy. And I go, what do you mean? And he goes, Mick, he says, when we sprint, he says that full suspension bike is like we're running on a mattress. He said, it's moving. It's like I'm running on a mattress. And he said, you know, I can't run on a mattress. I can't sprint on that bike. If I can't sprint on that bike, I can't race on that bike and win on that bike. And so that was kind of, you know, that was the punch to the gut where I really didn't have anything to counter, right? It was like he agreed it was faster in that technical climb, but I understood, I mean, it was right there, smack right in the face. Without that efficiency, that firmness to sprint, you know, for the sprints, but then also the accelerations that are needed, it was a no-starter. And so packed up, got on the plane, left Majorca, coming back to Morgan Hill, in kind of a little bit of a bad situation, right? Because I was challenged to get those guys on that bike, but it was on that flight home, I just kept thinking about his comments about running on a mattress. And we had spent so much time on the efficiency of the kinematics, knowing that the power wasn't sucking the suspension down like it does on a motorcycle. But we paid very little attention to the downward forces of the rider in the chassis, in the cockpit, and how that's exactly what he was telling me. It wasn't the kinematics sucking the wheel up, the power, you know, pulling the wheel into the suspension, which was so common in those days because we had that all taken care of with the FSR technology. But it was just that mass of the rider moving under those extreme sprint conditions. And so on that plane ride back, that's where the idea of the inertia valve and how to utilize that in a bicycle application, we could, you know, the thought being, and it's turned out to be irrelevant or true, is we can give him that firmness for sprinting and accelerations, but we can give him that open suspension for that technical terrain. So that plane flight home was where it hit me, you know, somewhere that opportunity, and I just worked on drawings all the way to San Francisco. The next day I came into the office, met Ben Caper and Mike Sinyard. They were going, okay, Mick, are they racing the bike? And it was that good news, bad news type situation I had to deliver. I said, I got good news, I got bad news. And they're like, well, what does that mean? I said, bad news, team isn't gonna ride the bike. I said, good news is I think I've got a good idea for some technology that will get them to ride full suspension across country. And that's laid everything out on the table. And they just go, right on, let's get going. And off we went.
Yeah. No, and to be clear though, and not to detract from your plane ride brilliance of having the idea, sort of the aha moment, being able to sketch these things out, but no, inertia valve technology is not necessarily something that was new even now. Certainly not. We've been implementing it for over a decade. But you touched on it. You mentioned it that for bicycle application. Yep. I think that's an important thing to touch on, to give a little backstory on what is the idea of the inertia valve. I mean, we have talked about it, and I feel like we've done it as a brand, as a company. We have explained very well the idea of the brass mast and covering the port, reducing oil flow, and how we can discern the rider input versus trail input. But like you said, this for bicycle application. So you, as I understand, had some awareness of inertia valve technology in suspension, kind of implemented in other ways in different worlds. Could you tell us a little bit more about that?
Yeah, exactly, Jared. That's correct. I didn't invent the inertia valve itself, and I had been aware of it. A friend of mine, actually, I was his mechanic when I was a young man up in Canada, racing. He was a motocross racer, factory Suzuki up in Canada, and then Fox sponsored Jim Turner. a gentleman named Jim Turner. He's the older brother of Paul Turner, who founded RockShox. And we all grew up together in a little town called La Selva Beach over here in Santa Cruz, racing motocross. Jim, brilliant engineer, and had been doing some work in the automotive space. And when he would come home, because we were all suspension technology and just motor technology, all that stuff, he had spoken of this inertia valve shock that he had seen and was working on, and he explained the inertia valve. And it's, I don't have a good example of it, but maybe I've got some parts here, right? But basically,
oh, Chance to the rescue.
And so he'll do a little flicking of it right there. But basically, it was this brass mass that's biased by a very lightweight spring, and it's nested in a position where when you're pushing on it, the valve stays in its nested position. The brass does. We use brass because of the density of the metal. But when it comes from the other side, that light spring, it's actually like the damper moves, but the inertia, the brass mass, stays behind, and that allows those upper ports to open. So again, I had remember hearing about that. He was explaining that it would differentiate between loads from one end to the other, but I never really saw a need for it in the work that I was doing. I'd always thought maybe it would be good for a motorcycle for brake dive or something like that, but I never really did much with it. And so that thing was buried in the back of my head somewhere. It was probably about a second or third rum and coke on the way home where it kind of, released it, right?
That's right. That'll tend to happen.
And that's where I pulled that thing out. But again, all of the stuff that, again, and I had studied a little bit, but it was always on the driven piston of the shock absorber, which would never do us any good. It was done on the rebound side and the automotive application. And so the idea that I had the design that I did was using that principle of the mass on the spring in the reservoir of the shock as kind of this gate valve that would keep the displaced fluid from entering the reservoir where the internal floating piston and nitrogen charge is. And by doing that, that basically keeps the shock from moving. And then if we activate it, it would open, and then the shock would go into the active mode. And so the other thing too that was unique about my designs on the airplane was that I would put it in the reservoir, and then I could move the reservoir down where I needed it to be active, which is at the rear wheel. And so if you look at all of the iterations, you'll see that either the shock placement was such, like we did on the early Sidewinder, so that reservoir is at the wheel. And then in later iterations, we use a hose, and then we have the remote reservoir down there. And it's for that reason, because we need that movement of the inertia valve, of the reservoir and the inertia valve staying behind for it to work. So that's, because we have patents around all of this technology for the application. And that was what we brought to the inertia valve stuff, was using it on the compression, separating, but out there on that reservoir. That way we can put the shock anywhere on the chassis that we need to, and then we can put that thing the reservoir where we need it to get it to function.
Just nothing short of a sheer stroke of brilliance or luck,
Those 3 rum and cokes.
Or 3 rum and cokes. Yeah, that'll do it. Heck. And so what I'm kind of taking from that is, hey, never underestimate the influences or the outside influences rather, and how you can learn from somebody else's experiments, designs, ideas, tweak some things a little bit, and figure out how to package it in a different way and find a home for a different application and increase relevance. And interestingly, maybe it's a theme for the conversation here, but let's put a pin in that, because I think we'll get to it a little bit later, but we do have another example of how that similar thing can evolve and move on. Maybe Chance can tell us about a position sensitive fork, but I would love to hear a little bit more of that story. So let's see here, Mick, we've got let's go back to this, and here's that Sidewinder frame you were talking about.
Yep.
So this was the first version of Brain as we know it, as we saw in production, at least, and this 2002. And hey, this was quite a feat to take that idea, that airplane idea, turn this into a practical application. Now, was this was successfully raced?
Yes, for sure it was. And we were able to convert, or convince, not convert, but I guess it's a conversion, but convince the XC riders on our team to race it. And they would race it in certain courses, and they would still use hardtails for other courses, depending, the XC courses were still evolving. But we were able to achieve that initial goal of having that system that differentiated between, again, that rider-induced forces from the cockpit versus what we saw on the trail.
Absolutely.
And when I see this bike and I see those shocks are prominent, man. Those are big, and that's a big old reservoir. But the Fox logo on it reminds me of the help that Fox on the project. When I came back, I had worked for RockShox prior to coming to Specialized, but I was good friends with both Bob and Jeff Fox. I had, as a young man, worked on their motocross team in the 70s, and so I knew both of them well. And so Bob, when I approached Bob, because we needed a strong partner to bring something like that, an idea on a shock absorber, Specialized isn't a shock maker, we're a bicycle maker. And so I had a meeting with Bob to see if he had any experience in this field and or if he'd be interested in helping develop these ideas into commercial product. And to his credit, I mean, he hadn't done any work in the space, but I mean, everybody knows how strong he was. I mean, he is as an engineer. He's done some phenomenal stuff over the years. But the best thing about Bob is he just loves engineering challenges. And so when we laid this out, it was like, let's do it. And so in the early iteration of that, he really was instrumental in kind of bringing that strong engineering and combining it with what experience and engineering and knowledge that I had, and together we were able to pull that one off.
Yeah, in a huge feat, right? And so as you said, there's been different versions, iterations of that. Obviously, that's the first one. So we saw that prominent piggyback that was attached to the shock. We hadn't yet evolved into, okay, let's make this remote reservoir hose. How do we do this? And how do you package it? But we definitely got there, and we started to see brain technology start to expand and blossom, right? So I'll show a couple of examples here just to kind of prompt us. So we fast forward, quite a bit. We've got the Rocker Link bike here, and you can see, this is definitely not an Epic anymore. This is a stump jumper. So now we are putting this brain technology on some trail bike platforms, getting a little bit more travel. We've got the reservoir there, and kind of change this up again with frame designs, stump jumper. But the point of all of this is that you and your team had started to expand the application of brain, and sometimes it worked really well, sometimes maybe not, but we always learned something, right? And I think as the saying goes, there's maybe an idea or a thought process that was, what's good for the goose is good for the gander. And when we have this overwhelming success in Epic and this revolutionary product, hey, it's got to be good for everything. So you went to work, we saw it, we implemented it across all sorts of things, but we also saw it, or at least nobody saw it, or you saw it maybe, on an enduro. And so at one point, really pushing the envelope, you started going down the path of putting this on the enduro. So what was really the end takeaway from that?
It was interesting because, again, it was, what this technology offered was a pedal efficiency, and it was really started based around XC racing on full suspension bikes. But because as we evolved it in the early days, we could see there was some pedal efficiency that even the longer travel bikes could enjoy. And even those stumpies you were showing they were called long travel back then, but I think those were only 120, 130 millimeters of travel, so they were pretty short travel. But you're right, there was this excitement and this technology internally here at Specialized, so we're trying to put it up and down the product line. But some of us in the product group were feeling that that technology is about pedal efficiency, and it's weighted, it carries it very valuable in this category, XC racing. But the problem still with the technology at that time, we got the pedal efficiency out of it, but the ride quality, just plowing through the bumps and all the stuff that's important in that trail category and that enduro category. Today's shock is a different story, because that thing will go head to head with any shock out there through the bumps and everything else. But back in those days, it still wasn't dialed. The whole system wasn't dialed like it is today. And so there was some compromises there. And so as we tried this, yes, there were pedal efficiencies, but then so we kind of moved away from it on the long travel. But the point that that I had shared with you earlier, on the enduro, when we were looking at it, the enduro, I mean, that the inertia valve technology, because it's got a platform, will take you to the top of the stroke, right? It doesn't know that you want, 30 minutes, you want a ride height at 30% of the travel or 25% of the travel. It just, the hydraulics will ratchet up to the top part of the stroke. So I knew to make it work in a long travel application, it would need something to address that. And so we had come up with a system in addition to the technology, to where we could get the platform of the brain, and we could program it through this tricky valve to have the platform at ride height. So it was a free travel up here at ride height. You would get that brain platform, and then as you hit a bump, the inertia valve would move. And so we had designed that originally as we were kind of marching towards maybe using it in the longest travel bike, which was the enduro. But then, like they pulled back. But Chance, who's part of the suspension team with me, was part of a crew where we did use it on one of the cambers, right?
Yeah, yeah. That was one of the first projects I actually worked on coming to Specialized, was that position sensitive camber shock. And it was actually one of my first introductions to brain. So it was pretty interesting to kind of come in at that point, and then kind of have that understanding of the technology, and then to kind of take it forward in something else, even though that had kind of gone away. Was something that was pretty cool.
That camber with the brain on the back was probably the longest travel version that, well, I mean, we had done the stumpies, but we kind of moved back away from that. And so that camber was where we tried it, but the camber model went away. And so we didn't really have a need for that rear. You come forward a few years, and we were looking at, what was happening and how the epics were being ridden. And that same thing, what I was learning when I talked to Ned over, and then I'd say, Ned, where do you run the brain for full firm? He says, no, Mick, I can't. I'm like 1 or 2 clicks off. And I say, why? And he's like, on the climbs, on those steep climbs, that fork will just stay at the top of the stroke. The hydraulics hold it there. And then that transfers more weight onto the shock. I'm sinking, even though I have a platform, I'm still oozing through a little bit. And then that front end it's not absorbing bumps, it's bouncing off. And so he says, if I open the brain 1 or 2 clicks, this was the old design, I can lean forward and get to ride height, which is where you set your spring. And then I got the right attitude for climbing. And so again, it was one of those aha moments. That technology that we had developed for the enduro, used it a little bit on the
camber. Yeah.
It was like, oh, we need that in the front fork only, because I know on the back, the XC guy likes it up on the, 100 mils travel, boom, they want it up there, boom. They like that attitude. Because again, we learned that through the Epic, that camber project. So we brought that forward, put it in the fork, and we've been using that on the last 2 generations of Epics, and it works really well.
Right. And that has, even over just the last two generations now of position sensitive brain forks, that we have seen some growth and some development. Chance, I think you've been really running point on that, and had your hands pretty deep into that fork and tweaking that and making those adaptations and making it what it is. Could you tell us a little bit more about that process and where we are with it today?
Yeah, I mean, kind of like Mick said, the position sensitive thing was something that a technology we already had, and it was kind of reimagination, not too much different than Mick's original inertia valve designs, where he was taking something that was already kind of known, but repackaging it in a really powerful way in a whole different application. So the fork was kind of a similar thing. You think about even going back to some earlier technologies like travel adjust forks and stuff, where they were kind of trying to get after the same goal of trying to actually sink the front end down, like Mick was talking about. So it kind of just made all kinds of sense. I actually have a cutaway of the position sensitive fork here in my hand, and I can kind of go through a little bit of what it really does. Everything is still brain. There's still an inertia valve, just like we have on any brain fork or shock. The difference is we have ports that are covered by this small little, you can kind of see that port that comes off there. Yeah. And what I'm pushing on is an internal floating piston that's in all of our dampers. It's kind of a genius way of going about it, because you have this guy that's already moving based on shaft movement. So that's where Mick and the other engineers went to work. We can actually tell how much shaft movement we need here versus how much shaft movement we need here. And that uncovers those ports at a certain position of the travel. That's pretty much how all the position sensitive stuff worked. But another cool feature that we added to the fork is a bit of an adjustment to that. It's internal. You have to pull the damper out, but you don't have to pull the damper apart to do it. So up here, this is a volume adjuster, and you can just loosen this lock nut and you turn this slug in or out, and you'll actually be able to adjust where that platform sits, because you're actually changing basically the IFP height by moving the slug of oil up and down. So that was a really cool one, because we've always kind of fiddled with what is the exact kind of position you want it to hit. And we've landed on a pretty good setup, but depending on riding style and conditions and what you really want out of the bike, now the consumer has a little bit of leeway to go up and down with that. They can actually even bring it pretty much close to the top of the stroke, or let it sink really deep into the stroke. So that's kind of one of the more latest additions to this.
Sure. Yeah. Specifically having that adjustability in the free stroke. Mm-hmm. So what, just so we have some numbers to leave people with, what are the exact numbers? You said you can, if you wanted, you could dial it almost all the way to the top of the stroke. If somebody was inclined to soften that up as much as possible, get as much free stroke as they can, how much are they looking at?
So it all depends on the initial build. So the way a production damper is built, you can get, like you said, close to almost topped out, like a non-PSB brain. And you can go probably close to 40 millimeters into the travel, which on a 100 millimeter fork, that's plenty and probably a lot more than you need to. But it can also be built differently. If you're getting internally, it all depends on how you set that IFP when you actually build the damper. So a service center or something like that could actually kind of manipulate that a little bit. So
okay.
A lot of tuning and adjustability with that.
Yeah. And the spring rate that a rider would feel in that free stroke, how does that correlate to, say just their positive air spring? Is it the same spring rate in that free stroke as it would be when they move past that and activate the inertia valve and really sink into the travel?
Yeah. Spring is still totally separate from this. So you take this whole damper out, you still have a standard air spring that's housed on the other side of the fork, the positive and negative chamber. So all that's the same. So when you're adjusting this, you have really no changes to that spring. So you still have a nice linear motion all the way through. It's just that hydraulic force that you're manipulating and where it kicks in. But that said, remember, it's still a brain. So it's when you get that platform, that brain still opens no matter where that platform is. When you hit a bump, you're going to default into the open mode, and you'll have a kind of a standard feeling open fork.
Sure. Yeah, well, that's super cool stuff. I mean, and so we're on the second version of this now. I see this fork out in the wild, and thanks for the opportunity of having that showpiece and speaking to it. I see it in the wild. I talk to riders, and sometimes it still seems like it's not fully understood you know, what we're looking to achieve, what the real benefits are of that system, and what the expectations are of that feel, because it is a little bit of a different feel. You know, I think from what people are accustomed to, they're, you know, most riders, as I understand, are pretty well used to maybe locking out a fork or something and just feeling it, you know, some hydraulic force right off the top. But it can be a little bit of a different sensation, you know, as you know, just, you know, sagging in a little bit and then hitting that threshold later.
Yeah, it's definitely one that requires some education, making sure people know what it really does. And we do get a lot of feedback from people that maybe don't know the technology, even just pushing on it in a showroom floor. And they might not even push into the platform, right? If they don't even step on the bike. And some people maybe think that the brain is not working or something like that. So one thing, if people are playing with this on the showroom floor, trying to showcase it to consumers and stuff, obviously the easiest thing to do is just really lower your spring pressures down so that you can push through the fork on the showroom floor. That's something that we do a lot for just showcasing. If you have 100 PSI in your SID fork and you're trying to push on the thing, you're not going to really be able to feel the damper and the system and the amount of free bleed that you have. So that's an easy way for anybody to kind of see it and feel it without having to get out on a ride. But obviously getting out and riding it's the best way.
No, that's a great suggestion though. And, you know, it sounds so simple. It could be perceived as kind of silly and stupid, but you know, hey, I think that's a great piece of advice and super sound. Don't set that fork up to your proper riding pressure. Just maybe take it down to 50 pounds or something, and really give yourself an opportunity to feel what the hydraulics are doing.
Yeah, just as a showcase, or say a bike on the showroom floor or something would be a good way
Yeah.
to do it.
Yeah, no, that's fantastic. And so that's a Rock Chalk's product. And, you know, but and that is brain. We're talking about brain. We're also talking about, at this point in the evolution of brain to kind of get us where we are. We've now moved from the Fox built, rear suspension setups that we had for a long time, and we've moved into the Rock Chalk stuff now. So this would be the prior version from where we are. And I like this photo because this just, you know, is just a super tight close up on what ultimately was a pretty radical change in the layout and the way that we were packaging this piece. Both, you know, either from IFP to a bladder, where that's positioned in relation to the inertia valve, as well as just the inertia valve's location in relation to the axle, which is, as we have found out, an extremely important relationship. Mick, could you tell us a little bit more about sort of the evolutionary process that led us from where it used to be in those earlier versions, kind of pretty far forward, to now here hanging it off the back?
Yes, sir. Well, you know, there was a lot that went on between these periods, but you know, the original concept was this valve that would give us that ability to differentiate between chassis loading and trail events. But we quickly learned to make the bike faster, we needed all the other technologies supporting it. And what I mean by that is you need the proper multi-circuit valving arrangements inside there so you can control the wheel stroke when you're in the active mode. And so we continued to evolve the function of the brain, but also just the capability of the whole shock absorber, spring, wheel rates, all of that stuff to make the bikes continue to ride better. The last generation of Epics that you showed in that picture there, on the front end of that design, we were really focused on what we call momentum carry. And that, you know, there's a way I describe it where, you know, the pedal efficiency gets you up to speed, and that's very important, right? And that's where the brain, it helps it just, you know, those accelerations, the sprinting, it's a technology that gets us up to speed. And what I wanted to do, and we did it on that generation that you showed, we really threw everything we knew about fluid dynamics and, you know, piston designs and high speed flow rates, all of that stuff to make this thing, once you were up to speed, that it handled the terrain in a way that you maintain that speed, right? That momentum carry that I talk about. Bad suspension setup, I mean, can scrub your speed off, right? If you're not absorbing and decoupling the events from the forward momentum, your momentum has to go up, your momentum will go sideways, right? All those things are scrubbing your speed. So when you can get the right amount of suspension travel, you don't want to understroke, boom, you're glancing, overstroke, you're doing this big suspension movement, you give way too much travel to the trail event. So that design, we put everything we knew at it, and you mentioned, I mean, there's the front end of that shock, I know, where we just focused on how the oil left that body through that, through that part there. You know, we had that yoke, and it's connected to the shock absorber. But if you look at the way that fluid flows, boom, it's just this beautiful ported hole leaving the shock body, bam, into that yoke, and then just it makes a slight bend, and then boom, just straight down that hose to the reservoir. And then we did the same thing in the reservoir to get the fluid to flow. It's all about keeping it kind of moving in a laminar fashion and keeping it from getting turbulent, too turbulent in its function. The bladder was introduced in that design. You know, we were having issues the generation and 2 generations before with floating pistons. The performance, you know, there's kind of a shuddering that can happen with those. A lot of the IFPs that were used in our bicycle industry, because everything is so compact, that their aspect ratio was, they're almost like wafers. You know, they weren't as long as they needed to be, and that you'd see a lot of wear in there. First off, when you take them apart after 100, 200 hours, you could see the anodizing, the hard anodizing gone. You could see that nitrogen was coming across the piston. Also that you could just see through the wear pattern that thing was not moving as smoothly as we would like for that momentum carry, bump ride, all that thing we were focusing on. So the bladder is something that is pretty common in a lot of motorsports shock absorbers. So I had a lot of experience with them from my motorcycle days. And again, I think there's other bicycle companies starting to use them in different applications, but we used it in that generation because it still gave us that small package that we needed. So we went bigger on diameter, but it gave us the smoother ride characteristics that we were out of for that whole package. Like I say, it was so much with this stuff. It's the sum of all the parts, right? We can't, in the old days, you could just throw one thing at it and boom, you move the performance needle. But today you've really got to have a design philosophy and then a design philosophy, development philosophy that really pulls the details out.
Absolutely. I mean, living in a world of minutia these days, every
We
little bit counts.
What do we call it, Chance?
What's that?
Pulling out the details.
Picking the flash shit out of the pepper.
He said it, I didn't.
I don't know if we're allowed to say that, but it's something we live by.
Hey, no, that's good. We need to know what our suspension team's living by. Those are true words.
Working on the details.
Right. And you talk about the sum of all parts and throwing everything at it, and that shot of the ported out shock extension, the link, and everything that you did to increase the fluid flow, and really help like you said, that momentum carry. And that also went into the damping circuits and how that particular version of brain fade worked. And could you tell us a little bit more about how that deviated from how the brain fade feature had functioned in previous versions?
I'll start it and then I'll kick it over to Chance, because that's really, I mean, that is his area of expertise. It's my area of expertise. It's the where he lives these days.
Well, he lives in a world of momentum carry. I've ridden with him.
Dude, he
Holy
wakes up at 3 a.m. worried about momentum carry. And the fact that he's doing it allows me to sleep through the night. So I like that. But anyways, what we were doing, the original brain fades, which was designed to take the nose off that platform, so that firmness that we could get when that thing was in the closed position. But in our earlier designs, that fluid that you were allowing to go around the inertia valve went around what we call the mid-speed valving. So, I mean, in the first designs, when that valve opened, the oil just dumped into the reservoir. There was no other valving or restriction, and those early shocks would overstroke terribly. So we put a valve in there, a damp plate, which has all the shims and the traditional valving. So when the inertia valve opened, the fluid then still has to go through valving and act like a conventional shock. But the brain fade on those first iterations of the mid valve, that brain fade would go around both the inertia valve and the valving. And so what would happen is if you went into a real soft position, maybe to make the brain really soft, you were actually taking away the mid-stroke valving as well. So that wasn't the right solution there. So 2 generations ago, what we did was the brain fade is just free bleed around the inertia circuit, but still has to go through the valving. And then the free bleed in the valving stack is something that's fixed in the system, which is a common practice. And that really helped it, so that the brain fade truly just affects the inertia valve, the curve that you see in the closed position versus the transition to open. And regardless, then when you open the valve and are hitting bumps, you have a stable damping value that you can predict and know what's going to happen.
Sure. So you have some continuity in the ride feel. You know, ultimately, when you're at trail speed, going over bumps, whether it was, open, the brain fade open or fully firm, if you're hitting bumps and you're activating it, you're going through all the circuits with its firm. If it's totally open, you still have the same thing. So ultimately, the rider has some consistent feel and feedback and expectations of how the bike's going to behave.
And this would be a good time for Chance to talk about how, when we design these new generations, how he goes about testing them. I mean, he does a lot of testing with the brass out.
Yeah, you can really think about it. Imagine, like Mick said, you take the brass out of these things, and these shocks and forks still have everything that you'd have in a stump jumper or enduro. And for myself, I do a lot of work on, I work on the RX Tune program, which encompasses all of our suspension bikes, including brain stuff. So I do a lot of work on bikes without brain. So coming into the brain stuff, I took a lot of that and that mentality of saying, this stuff needs to ride just as good as a stump jumper from a damping perspective and a ride dynamics perspective, even once the brass opens. The brass valve, which is the inertia valve, is the technology that gives us that open close, the difference between pedaling and all that. But once it opens, which when you're descending, when this stuff's working really well, you're open most of the descent when you're in rough terrain or even some rough climbs. So I'd say that's one of the biggest things that I've worked on, especially since this technology is not new, and Mick has spent years and years dialing in the actual function of the inertia valve from EN coatings and all that to get it to work the way it does. Kind of allowed us to not have to focus so much on just the fact that the inertia valve won't hang up and all that kind of stuff, and allow us to just tune air springs and tune the damping beyond that. So to Mick's point, if you look at the inertia valve that we're always talking about, I can actually take that, just this piece, take it out, and I can build the fork and the shock completely together without it. And all it does is just allows these ports to be open the way it does when the inertia valve is open. So it allows us to go, for one, dyno the stuff on our suspension dyno. We can build damping curves just like we do on any other shock. And then we can ride them just like we do any other shock. Obviously, you have to decouple yourself from the fact that this will be an inertia valve bike. But we're able to really understand all these different damping speeds that we see. One of the biggest things we started identifying was the high speed numbers that we see. And when I talk about high speed, I'm talking about high shaft speeds, usually on square edge bumps and stuff. When the inertia valve opens, it opens these ports, but you still get into other valving. Even the hose can be a restrictor in some ways. So we were able, once we took the inertia valve out, we can run dyno curves. We see what the damping profile looks like without it. And we saw that we were producing a good bit of high-speed damping. So getting into the field, doing what we normally do, collect some data, understand the shaft speeds of certain trail events, knowing that the inertia valve is open, that's the number that we're seeing. And we started manipulating it. just the way we do. It's bendable shims. We have a spike valve in a lot of these shocks, and we go about tuning them. And even in the new shock, a lot of people wouldn't really think of it as a tuning feature, but what we did, like I said, the hose can be a restrictor in some ways. We actually downsized the shaft from 12 millimeters down to 10 on the 21 shock that we just developed. And that was actually mostly driven from a tuning side of it, because what happens is the shaft size determines how much oil you're pushing out to the brain reservoir. And at low speeds, it's not really a big deal. You think about 10 guys trying to run through one door. If they're all walking slowly through it, there's no restriction. But if you shove them all through there at the same time, you're going to get a backup. And that's kind of what we were dealing with. So the 10 millimeter shaft actually allowed us to basically send less oil at those high speeds through the shaft or through the hose, reducing our low speed or high speed numbers by quite a bit. So that was a huge one on our momentum carry for descending. When we're getting those really high shaft speeds, you get much less hang up through that. That's one of the ways we went about it. It's kind of an interesting way. Usually we're tuning with shims and all that. But,
so you're telling me that you reduced the shaft diameter, that ultimately reduced the amount of oil flow to push into the system, but that increased its ability to handle high shaft speed situations? That almost sounds counterintuitive to me. That you're restricting, it sounds like you're restricting oil flow, which sounds to me like that would be like a hydraulic lockout sort of situation.
Well, if you think of it, we reduce the shaft size, which reduces the amount of fluid that it has to push through that. So it's kind of like, think about the guys running through the door. If we were sending 10 guys through a doorway and they're getting jammed up, we reduced it down to 5 guys and they're able to get through a lot easier.
Okay.
So that's kind of the way it works.
I see.
And it's only on a high speed value that was really important. Like I said, at low speeds, we're sending the same amount of fluid out, but we're sending them through at a slower rate. So the hose just being an orifice, or you can think of it as a door, like I was saying, it's not clogged up if the oil's moving orderly and slowly. Mm-hmm. So that's where that kind of came in. So
absolutely.
That's one of the cool things about us being able to own the design of the shock is we're able to tune those kind of things beyond just bendable shims that we wouldn't have been able to do.
Absolutely. Yeah, no, that's incredible. And this is, like you said, this is coming as a result of you putting the time and sort of out of the box thinking of pulling the brass out and testing these things in a variety of different ways. And, that's super cool. And ultimately very impressive to where we are. So, and what you were just talking about, that is relevant to the latest and greatest, the MY21, right?
Yep. Yeah, we prototyped it based on the old, or the 18 shock, which I guess we can call it the old bike now because we got a new one.
That's right.
Yeah. But yeah, we actually prototyped the smaller shaft to prove this all out. We made some samples, and most of it was done on the dyno, just putting a small shaft in there, had to redesign a seal head, and we were able to get the values we needed.
Yeah. And so we've got an image of the new package here. Again, a bit of a departure from the last radical departure we had, but this one is super exciting. I mean, run us through some of the changes, or heck, all of them. We've got some time. That this is unlike anything that we've done before. I mean, as I understand and what I felt shoot on the trail, this thing, it's unreal how well this performs, which is admittedly exactly what I said about the last version compared to the ones before that. But this is absolutely next level. Aesthetically super pleasing. Now, big change, of course, we're back to an IFP. It's packaged in a little different way. So tell us a little bit about that, and let's get into some durability statements and just general fluid flow and fun suspension nerdiness.
Well, I'll tell you on just one of the visual things you'll see that the layout's a little bit different. And it's a stepping stone of that fluid flow and reducing any restrictions, or Mick would kind of consider it a turbulent flow versus laminar flow. Again, we're trying to allow the fluid kind of the least path of least resistance. The fluid obviously running through the hose, it goes directly into the inertia valve and then the spike valve circuitry, but it ends up having to end up in the IFP chamber, which is now housed in the chainstays there. So it's a really direct flow path rather than having to make lots of bends. It's something that obviously we talked about a little bit on the extension from the 18 bike. That was a big move toward reducing some crazy flow paths. And then this is another huge step forward in that, and really just creating the flow path that goes straight into the IFP and straight back without much bends and turns, and ability for the oil to hit sharp edges and things like that.
Yeah, and then we've got the repackaged IFP. It's a much longer cylinder, a smaller diameter, right?
Yeah, I'll talk to that one. So again, when you go back a generation, we had the Epic, and I think we had an Epic Evo version of that, but they were all based around the same platform. So if you actually look at what we were doing with that shock absorber, we were actually pulling the platform down a little bit to the point of where we felt like we had the pedal efficiency that we wanted. But then again, that big focus was on maintaining that speed and all those other tricks that we were doing to make the shock work better. So the bladder kind of lended itself to the mindset of that, and again, that last generation on being something that was more trail worthy. But a lot of the feedback that we got back from the racers and a lot of the really serious cross-country type riders was that that platform wasn't firm enough. And so when we set out with a new project on the bike, I mean, the bike, we have these performance goals that we establish, and on the shock absorber, to Chance's point, one of them was we still felt like we could make the momentum carry, the ability to hit these very high frequency events and stuff that work better. But at the same time, we also needed to move one of the targets for performance on the shock absorber was we needed the firm platform, firmer than what we had. And so we did a lot of testing with our team, our race team, our factory race team, and then also some really good riders out of the southern part of Europe and Italy and France, where they really love the Epics and ride the Epics. So we reestablished what that platform should be. But the other part of that was we really wanted to make that transition of the system from the firm position to the open position smoother. It can get kind of chunky when you're holding all that hydraulic pressure and then boom, you open up the gate and it goes. And so we were doing a lot of things to make that transition smoother. So the 10 millimeter shaft helped us. I was concerned about the 10 millimeter shaft. That's why we jumped on it early, like Chance was saying, because that would have an effect on our ability to make a platform. So the first thing that we did, we knew the benefits in the higher frequencies going to the small shaft, but we needed to make sure we could make the firmness. So with that, so now, okay, we ratchet ahead to this new design. So I was talking about performance goals. We split it again. We have an Epic Evo and we have the Epic Race. And the Epic Race, so we made the decision that the brain technology would be focused for the World Cup race, the Epic Race bike, boom. So it allowed us to really focus the performance. And one of the things that we wanted to do was make the shock firmer, get that platform firmer. And the bladder versus an IFP, if you look at, there is a little bit of an internal spring rate that is made when you compress a shock that has 100 and 200 PSI of nitrogen in it, right? You take the spring off and you can actually pick up a slight curve. It's slight, but it has an effect on the overall system. The IFP, the floating piston, has just a good old fashioned air spring curve where the thing is, it's holding back the pressure and then it bends and goes. The bladder, on the other hand, it starts compressing slowly and has a little bit more of a linear, a softer nose to it as you start moving the shock. One is good, for the kind of that trail experience. This other one, the floating piston, knowing that we were changing the design, and I'll get into why I felt comfortable going back to an IFP, I had described some of the issues we'd seen on the generations, 2-3 generations ago of the floating piston. So we could get that kind of that nose that we liked to help us in that, giving us that firm platform that this new shock has, but also get that smooth action. So when you go to the new design, we've got a reservoir that's really long and small diameter. And so the floating piston, I don't know if you have a cutaway, Jared, or not, but it's a very long floating piston by industry, like by bicycle industry standards. It's got a bushing on both ends, and then the seals in the middle. And so it's got a really favorable aspect ratio, meaning its length is really long compared to the diameter. For the other ones that we were fighting, like I say, 2-3 generations, it'd be 3 generations ago now, they were really big diameter and they were really flat. And so those are the ones that will kind of do that action, and that affects, the shock action. It becomes kind of skatey, shuddery in its own action, which then you feel that at the wheel versus something that's really smooth. This good aspect ratio, boom, really smooth, gives us kind of a little bit of a nose that then helps us. Obviously, there's other things that we do inside that shock to get that thing to feel firm and have that snap that the XC guys racer wants. But that was just one of the things that helps as well. So kind of a refocus on just pure race, boom, allowed us to kind of just go in a direction and not try to take one shock design and do too much with it.
Absolutely. It's seemingly always a beneficial thing if you have the luxury of having a narrow focus and really attacking for progress in a specific, simplified, end goal, right? And what I'm hearing is pretty interesting to me in terms of hey, you change one thing with really good sound reasoning. There are many implications on down the line that to kind of go back to what you said too, of the overall performance being the sum total of all parts. You change your shaft diameter to solve for one thing. Well, that's going to have an inherent different characteristic that may impact how firm your platform could be. Then you need to change this to compensate for that, and it kind of keeps coming down the line. So you guys are really, it's a significant challenge is what it sounds like. And you guys have you've risen to the occasion and we're come to market with a great system here. And so durability, this is a big statement with this, and you touched on it with the smaller IFP diameter, bushings on both ends, across the board, and that's all specifically the reservoir and inertia valve side of things. But we've also addressed some durability concerns that we've seen in the past up in the main shock body as well. Maybe this is a good question for Chance, if you can speak to some of the measures that we've taken there.
Yeah, definitely. So kind of along the same lines as Mick was talking about with the IFP, we know there's things that we didn't like about the IFPs being so thin and narrow and not being guided very well. So totally rethought it and really guided it well, better than anything we know in the industry. And we took that same kind of mentality up to the driven piston on the main shaft, the front part of the shock. So that guy slides on that 10 millimeter shaft. And through frame designs and all that, packaging always kind of gets shorter and shorter, and usually that eats up a lot of your space to really guide things well. And we totally went back the other way. Double guided bushings. So there's bushings on both ends of the shaft seal. Again, like bigger aspect ratios than you see on any metric shock in the market. Yeah, there you go.
I'm gonna help you out here, buddy. I happen to have one on my desk. So this is a cutaway of it. And to Chance's point, the traditional seal head, and this goes across most models that we use in the industry today, the seal head's about half of this distance. And to Chance's point, we knew where the issues were. These shocks The strength of the shock, because you get in, especially, you know, to be honest, it's probably the XC bike puts more loading on a shock than an enduro does, or a demo. You would think it's the opposite, but those frames are so big and strong. They isolate the shocks. Like if you look at our enduro and our demo, there's no loading going into the shock, but they're able to do it with all the structure and stuff. And when you start getting down to these super lightweight bikes, you know, you're seeing more and more of the loading going into the shocks. And so that was one thing that we said, you know what, this thing needs, that's where we need to focus on this thing. So Chance's point, what we did here, we went to a steel shaft. When we shrunk it, we always used aluminum shafts, lightweight and everything. And this is one of those things where I said, guys, what is that saying? And there's another one of those sayings, ounce of prevention is worth a pound of cure. Is that it? I said, dude, I want those 2.5 grams on that steel shaft. I'll take that, and give me a friggin' steel shaft, please. And then we just said, I need, you know, 1 inch on the dead length of the shock absorber, because I'm going to put it in the bushing and also on the air sleeve. If there's an air sleeve seal that goes here, same thing. We put a bushing, and then buried the seal in between it. Really give it a nice wide distance. And believe it or not, this little piston here is wider than most of them that you would have seen in the design. So we said we need some dead length in the shock because we're going to put it in. And what this does is it just makes the shock just really, really stiff to the loading. And what happens when you load a shock, and this is anything, you know, it can be a motocross bike. Motocross forks have that. That's the kiss of death, is that, you know, that flexing and that loading. When that's happening, you know, that's what allows the grit to get into the seal. And that's what allows air to get into the fork. You know, when those things are in different times of the stroke and they're being loaded one way or the other, the actual seal, you know, and on paper it looks great because it's you know, it's loaded concentrically. But when you load it one side, you overload the seal here and you underload it here, and then it's compromised. And so by taking this approach, which is unique to the industry, that oil seal is protected from oil leaving or compressed air on the air spring side, because this is an air shock. That's another thing that can happen. You know, you load a shock, and if the radial runout can get to the seal, the air can come back in, and we would see a lot of that on Epic shocks as they got time on them, that, you know, you actually would ingest air, and then on an Epic shock, that's the kiss of death, because then you have a gap in your platform. Most shocks are doing the same thing. They're ingesting air, but they don't go back to this locked position, and you don't even know that your shock's emulsifying.
Right.
So
unless
all
maybe
of
you have
that
a very
stuff,
keen
what it
ear.
does, so by doing that, it just makes it so that the radial play, you can load it and you're not getting that loading of the seals that allows, again, grit to get in. And more times than not, what wears out an air sleeve, why they need air sleeve service, is because they're seeing this stuff, the grit gets in there, and then next thing you know, it's compromised, it's caught up on the O-ring, and then the stuff is leaking. So that's one of the things that we did with this new one. Testing of it was just phenomenal with regard to air sleeve service and all that other stuff. So we bumped up the intervals. Chance might be able to help me with the numbers. I've been in enough. I know it's 250s on the damper.
Maybe 125 on the air spring now.
We went from 50 hours, you know, which is kind of a standard for a lot of them. I mean, it all has to do with when you guide it as strongly as we did, again, with these double upped bushings and put the seal in the middle. We just it does a really good job of stiff shock, keeping the contaminants out, and you can just go longer.
It sounds simple, but, you know, I know there's so much that went into it. And, you know, hey, a word that comes to mind that may not typically be associated with this type of bike and product was robust.
Yeah.
This thing sounds incredibly robust.
And, you know, Jared, there's one thing that's worth mentioning too on that. There is a performance aspect to that steel shaft and those guided bushings as well. We started doing a lot of this testing in our lab. We did a lot of load testing where we would heavily load these things. I'd have these shocks bent up in the lab.
I've seen it.
And I'm running these damper tests. And we were doing a lot of it from a durability standpoint, but me being a tuner and looking at these numbers, I was actually seeing, as we were heavily loading these things, essentially like damping numbers were increasing by quite a bit when we were loading the shocks heavily, you know, equivalent to like 2 bracketed tunes up from where we where we would be normally making it unloaded. So in a way, you would have these events where you would load the shock, and under compression, you were actually over damping based on friction. The double guided bushings really help this, but also the steel shaft. It doesn't seem like the sexiest material for an XC racer maybe, but any suspension guy will tell you that there's no surface finish better than chrome steel. Even beyond any type of coating you can put on aluminum, there's really nothing better. And then the way that we guided it, those load numbers from a performance standpoint made a huge difference. So it's kind of twofold. It wasn't really meant to be a performance. I think that was kind of in the back of our minds, but it ended up helping quite a bit.
But hey, this phrase will make its way twice into this webinar. What's good for the goose is good for the gander. No, that's fantastic. And what else is going on in that air spring? And we're about up on time, but we do, as I understand, we've got some more adjustment options going on in this air spring as well than what we've ever seen before. Can you speak to that a little bit?
Yep, definitely. So one of the big things, obviously, we've gone away from auto sag, and we've kind of gone away across the board as a company. Not because we didn't like auto sag, but as we started really developing things, for one, there's a weight aspect to it that the product guys like to drive. So it is a lighter system without the auto sag. But we also really started doing a lot of tuning with the negative spring. Auto sag relies on a specific transfer port location and negative spring size to work correctly. So in a way, to get auto sag working the way we want it, we weren't able to get the spring working the way we wanted it. So made kind of a tough decision to go that route, but once we did, it just opened doors and allowed us to really kind of just explore different air spring tuning options. So we have a little bit larger negative spring, a little bit deeper transfer port, which helps with a little bit of suppleness. But then we also added a negative spacer in there, comes stock in the shock, and it's something that you can remove, and that'll manipulate the air spring a little bit. You can change kind of the initial nose of the spring curve, but it'll also change the ending part of the stroke, similar to a positive volume spacer. So it works the opposite of a positive volume spacer. So as you take one out of the negative, it's going to make it a little bit more progressive. So some small features, but a lot of where it came from was the ability for us to tune it from a design side.
I see. And man, that's awesome. Thanks for explaining that one a little bit. That can be a little bit tricky, for people to wrap their heads around too, myself included. But across the board, shoot, we've got a lot of fun things to talk about and share. Thank you guys both for coming on and giving us Mick the history lesson always. Maybe next time I have you on, you'll be Professor okay. Mick.
I like it.
Yeah. And Chance, always wonderful. You guys are hard at work, always thinking outside of the box, always trying different things, pulling ideas seemingly out of your hats. Maybe sometimes they are, maybe sometimes they're, long overthought patents from the automotive industry from a bygone era, but nevertheless, it's always exciting to see old ideas come to light in new ways, as how we're experiencing these products and what the forward generations of riders, how they interpret trails and their bikes and everything. And so totally thrilling that we're constantly on the leading edge of this, thanks to both of you guys and your hard work.
Yeah, thanks for having us.
Yeah, you bet. Okay, well, enjoy the rest of your day. We'll catch you later. Thanks, everyone.
Thanks, Jared.
See you, Jared.
Bye.